Okay, we already have a perfectly good way of describing surfaces in 3-space with z as a function of x and y, but for some purposes we might not necessarily want to have 3 variables. We might not want the number of variables to match the dimension of the space. We might want it to match the dimension of the object, and it's a 2-dimensional surface. But I could still use this. What I can do is basically just introduce my parameters, which I'm going to call u and v, but then with my parameterization, I can just let x be u and y be v, and then z becomes a function of u and v. So my function r of uv is just u, v, f of uv. So it gives me a way of using just 2 variables rather than 3. Now what's kind of neat about that is that then I can see a geometric connection. Because if I just took this uv plane and I moved it into 3-space, aligning the positive u-axis with the positive x-axis, and the positive v-axis with the positive y-axis, I'd basically just be attaching a height to various points. So as an example, if I have z equals x squared plus y squared, I can parameterize that as r of uv equals u, v, u squared plus v squared. So if I already have a function that describes my surface, I can use that to come up with a parameterization. Now, this is going to be limited to surfaces that pass the vertical line test. The sphere is not the graph of a function of x and y because it fails the vertical line test. A point xy would have more than one z value associated with it. But this is a very nice way of describing things. Now, if I can do that with rectangular coordinates, I can also do it with polar coordinates. Okay. So here we were looking at z equaling x squared plus y squared. I could also have something like z equals f of r theta. If I want to look at the same surface, x squared plus y squared is just r squared, so theta doesn't happen to show up in the formula. So it's actually exactly the same graph here. Now, I'm probably going to use as the names of my parameters r and theta rather than u and v. Okay. I kind of like to have different names than x and y because x, y, and z, that's in my 3-space. Different names, that's in the 2-dimensional domain for this thing. Although there certainly are times when, if I'm letting x equal u and y equal v, there are certainly times when I don't bother with this change of names and I just say x is x, y is y, z is f of x, y. For now, let's agree that we're going to use different names for the domain in 2-space than we use for what we have in 3-space, at least until we get comfortable with this. Okay. All right, so then I would say r of r theta. Now do be careful here. It's not r theta r squared, it's r cosine theta, r sine theta. So I'm describing x and y and z would have been r squared. Okay. So if I'm using polar coordinates, I'm not just putting r and theta here the way I can if I'm using rectangular coordinates, because as we parameterize, we are always describing the rectangular coordinates x, y, and z of our point. Now, that's not to say that we couldn't invent a different system where we were describing the cylindrical coordinates of our point. But that's not the system we're working with. We are working with parameterizations that describe the rectangular coordinates of our point. And that's going to be important. Right now we're just trying to describe the surface, but eventually we're going to start to do things with those surfaces, and it's going to be important that we're consistently describing x, y, and z. Not sometimes this is an r value and other times it's an x. The first coordinate is always an x value. Okay, excellent. So I mentioned that we were going to have several options for how we could describe a cone. So I want to just take a look. If I've got z equals the square root of x squared plus y squared. Okay. So that just gives me this lovely half cone here where my z values are non-negative. Okay. So I could certainly describe that as r of uv is equal to, let's let x be u, let's let y be v, and then we would let z be the square root of u squared plus v squared. Okay. So I can take advantage of the fact that, great, that was a function of x and y. But this means that z is also, if I work in polar coordinates, z is equal to r. Particularly if I'm working, well, in this case, it would have to be with the restriction that r is bigger than 0. So when I was defining the domain of this transformation, I would have to restrict r to being non-negative. If I didn't, I would be getting a double cone here. But I can do that. Okay? I can say r is going to be bigger than or equal to 0. And then I could describe this as r of r theta would be r cosine theta is x, r sine theta is y, and r would be my z value. And I would just have to make sure that I specified, because there's nothing inherent that says that r must be non-negative. I know if I'm integrating in polar coordinates or cylindrical coordinates, r must be non-negative. But if I'm just using it in describing a shape, I would need to specify that I'm putting some restrictions on it. Okay, excellent. Notice here, this would map the entire UV plane to the cone, because the entire XY plane can be plugged into that formula. Okay, this would map half of the plane in the r theta world. So in the UV world, the entire plane maps to the cone. In the r theta world, this half plane is what's mapping to the entire cone. And the third option that I would have would be to use spherical coordinates, because a cone is a constant phi surface. So if I want to figure out what the phi value is, so here's my constant theta half plane. That's the z-axis. This is meant to be the xy plane. So it's coming out from the board like so. The cross-section I would see would be something like so. But I know that z is equal to r. Well, that tells me that tangent of phi is going to equal 1. Phi is going to be pi over 4. So this particular cone is the constant phi surface where phi is equal to pi over 4. So I could say now I can describe this in terms of rho and theta. So remember, in general, x is rho sine phi cosine theta. Y is rho sine phi sine theta. And z is rho cosine phi. Now all I'm doing is replacing phi with pi over 4. So my x value would be rho times sine of phi, would be sine of pi over 4 is root 2 over 2 times cosine of theta. Y would be rho times sine of phi would be root 2 over 2 times sine of theta. And z would be rho cosine of pi over 4 would be root 2 over 2. So that's 3 different parameterizations of the surface. For this one, if I looked at the rho theta plane, I would be, if I wanted to get the cone once, I'd basically be looking at this infinite rectangle. Let theta vary from 0 to 2. Oh, and actually over here, I'm sorry, I didn't want just that half plane. If I can let theta vary infinitely, but if I do, I'm going to get the cone multiple times. If I want to get the cone just once, I would let theta vary from 0 to 2, and r be non-negative, so I'm looking at that infinite rectangle mapping to the cone. Here it's very similar. I want my rho to be non-negative. Okay, that's its role in spherical coordinates. And if I suddenly allowed rho to be negative, I might start getting cone down here, which I don't want. Okay. If I let theta vary between 0 and 2 pi, I'm going to get that cone just once. If I let theta vary further, I just get multiple copies of the cone. Kind of neat to have all of these different options. I think that one tends to be the nicest one to work with. I'm never crazy about having a bunch of square roots in my formulas. I really like that because that's just r's and thetas. This one's pretty simple too. So I think either of these would be a better option than this in most cases.